So, what we did last week was we started our work on sensors. Basically, how to configure sensors for use in an app, and we in fact implemented the functionality of one of the sensors, the ambient light sensor. So that was what we did. For some reason, it doesn't let me close this bubble, which is covering my screen. Okay. All right. So I just want to make sure that a couple of things are clear and out of the way. One is about the group project. So I said that week 3, you have to submit your topic. I'm going to open a Blackboard item for that, for the submission. To be able to see that, you all need to have selected, your teammate if you're working with somebody, and then also self-enroll in a group. Have you had a chance to do that, to self-enroll in a group?
Yes, Professor.
Okay. So yeah, even if you are working alone, you must enroll yourself in a group, and that will be available to you as, let me just see. So I see that only one person has enrolled in a group. The rest of you have not enrolled. So please enroll, otherwise you won't even see the assignment for the submission. So yeah, so just how did you do it, Sandeep? Can you please just mention it so your friends know how to get there?
Just go to tools and my groups and then select group.
Okay. So go to tools in this here.
Yeah,
Okay. So then you find my groups and enroll in a group
like
like
just
this.
groups.
Groups. Okay. Okay. And then you can enroll in a group. So please go ahead and do that, all of you. That way, the assignment will become available to you. And then once you submit your topic and a little description, a brief description, I will outline what you need to submit in the Blackboard item. Basically, like a half page or a one-page write-up, whatever. If you want to submit a sketch of what the app, a rough sketch, hand-drawn is also okay. So that we know that, it meets all these criteria and it's good to go. Okay, that was one thing. The other one was the homework that you guys had last week that you had to, well, you submitted it. It was based on the first lecture we had, app widgets. And some of the items I had said by default that we'll discuss it in the class. So we had 3 questions. Many of you got all 3 of them right. The first question was about the difference between a frame layout and a relative layout, why we did that change. So what happens is, in a relative layout, it's like, you can tell the view as you're placing it, whether it's going to be below something, some other view, to the right of it, to the left. Basically, relative direction of it, and that is how the relative layout places the views. Whereas frame layout, the views are layered one on top of each other. And you can choose to show one, or if you hide the top one, the one that is below will be shown like that. And in our case, we have a combination of that going on. We are using a stack view, which already is a stack. And on top of that, we embed it in a frame layout. The reason we did it is because we want that empty view, instead of being relative to the stack view, it is behind the stack view. So it stays hidden unless the stack is empty, in which case it is shown. Second question was, and I think almost all of you got it right, why it keeps saying example, because this is basically a preview image. So this is one thing to also learn, that anytime you create an app widget, you must also create a preview image and replace this example image with that so that your own app's widgets preview shows here. Like we saw the other app widgets that are available, the ones we saw in emulator as well. Let me just run it here and we'll see. So those ones are, they all have their preview images. That thing is not being constructed live, that list of widgets. Right? So let me go there. This was our widget demo anyway. Widgets. So all of the images you see, these are actually preview images. It's got nothing to do with the calendar on your device, for example, these two. So this is all images, and just like that, we must have an image for our own widgets. Otherwise, it just keeps on showing example. So that's the purpose. And when you're doing your project, if you're choosing an app widget as one of the features, you will have to create one. The third question was, we had some unfinished coding. Basically, how do we make it so that if the image stack is empty, then if there were no images here, then it should just say empty. And many of you also got this right. So basically, you only needed to add one line of code which says that set empty view for what? For the stack. So if the stack is empty, show the app widget text. This is what you needed. And I it's also, I saw that some of you also renamed these appropriately, which is a good thing. So it makes the code more readable. So you may have changed the IDs to make the code more readable. That is excellent. So this was our homework for that class. Any questions from anybody?
I actually have a question. So for the preview image, is that a possible way like to automatically to update? I mean, like for example, if I do some change with my app.
Yes. So you want the image to be updated based on the change you made to the app automatically?
Yeah.
No, you have to take another screenshot or somehow create that image and replace it in the resources.
Okay, cool. Thanks.
Yeah,
Mhm.
it's coming from here, right? Example, I think this is the image. So you
Yeah.
can name it. If you rename it, you have to change wherever else it's being, set. And that's it. Good question.
Thanks.
Anybody else? Okay, let's continue. Sensors. So let me open the project from last time and we'll just do a brief review of what we did so we refresh our memories. Okay. So this was the app we were working on last time. You can open your own. And what it does, where did we stop? We stopped at the point where we could change the light meter readings and see the effect. Is that where we stopped? So run your app and see if this is where you are right now. So when you run it in the emulator, you will see the app here. And you can pop expand the sensors. Yeah. Virtual sensors. Okay, these were our sensors, and we had this implemented. So once we change it, we make the light right. This is what you should have, and we used a threshold of 5,000. That's what I used. You might have used something else. But basically, Michelle, you're talking about this panel on the left or the emulator? The panel on the left, you click these triple dots, the menu. So to the side of your emulator, you should have this panel of buttons in the bottom one. And it did not come up right away for me. It took a while. So you click it once or twice and then it takes a moment to come up. And we have a delay. We are checking for the light sensitivity at a certain frequency. So as soon as you change it, it does not take effect until the next update in its cycle comes along. Okay, everybody is able to do that. So before we move on, anybody not able to do it, please, you need to say more than those who can do it. Okay, what are the participants in the class? So the rest of you, almost everybody is here. Anybody having difficulties with this, not able to change the light sensitivity and see the effect? Okay, good. So how did we do that? Anybody want to describe the steps we took? What were our steps in the code? Anyone?
So the step we did at first, we have implement the sensor event listener, right? So we create the sensor manager to get the specific the sensor to control the tap light. Then with that, we implement the function on sensor change, which means if the light change, then we do something with our screen.
Perfect. That's exactly what we did. So we have to, those are the exact steps. Your You can use it the same activity, you can create a different activity, not necessarily an activity, you can create a different class which does the job, but it must implement this interface, sensor event listener, and that requires these two methods to be implemented: on sensor changed and on accuracy changed. And we declare these variables, sensor manager, light sensor, and we retrieve them in our view on create method. And once we do that, we have access to these. There's one more step here. We have to tell the sensor manager to start sending the events. We have to register every sensor we want to listen to. We must register this activity, our listener, because we have implemented the listener. Main activity is also a sensor event listener. So we tell the sensor manager that our current class is going to be listening to the light sensor at this frequency. And we do that on resume. So whenever the activity comes to the foreground, we start listening. And on pause, we unregister, we stop listening. So if the activity goes into the background, another activity replaces it from the same app, or the user presses the home button, switches to another activity. Any of those events will cause on pause to be called, and we will unregister. And then the next time the user comes back to that, it will again register. This is good behavior. Android expects you to do that, to not continuously be listening even when you don't need it. Now, some apps listen continuously, even though they are in the background. Can you think of one? How about when you are navigating, taking directions, and if your maps is in the background, does it keep listening for the GPS location? So that would be one example. That even though because that app then is not doing on pause unregister, so it keeps listening. So if your app is doing something like that, if you're implementing, let's say you're implementing a step counter, then you would keep on listening even though the user may have switched to the music app, for example, to play music. So depending upon the case, you don't necessarily have to do it, but if you don't need it, then do this. Okay. That's what we did last time. This was, we went through the documentation. We have looked at the light sensor. These were our steps. We just talked about them. And we also saw how to work with sensors in the emulator. So that's one good thing about Android, that it lets you do all of this. iOS does not. The iOS simulator has a problem, exposing sensors. So there we are going to have a bit of a challenge. Okay. All right. I think we stopped pretty much there. We may have started talking about this, but I will resume from here so that we have a logical flow today. One other thing we did last time in this was to not be processing every event that was being sent. We were getting like 4 or 5 events per second from the light meter. You might still be getting it. I don't know if we have it commented. We don't have it commented. So yeah, we are still receiving, but now we are processing at a certain interval, which is processing interval. So we keep track of when we did the last processing of the event, and then we let this much time pass, processing interval, which is 5,000 milliseconds. So every 5 seconds. Makes it easier if you extract everything out and declare in variables. And if you want to change this, you think 5 seconds is too slow or too fast, you just have to change one number and you're good to go. All right. Motion sensing. So let's look at the documentation. The link is here, and I actually have it open in the next tab. So motion sensors, the two main things are accelerometer and the gyroscope. These two are hardware-based sensor, and these two allow us to calculate a lot of things, and those things may be exposed as software sensors, like many of these may be software sensors. So what a software sensor means is that you get a reading from the accelerometer and the gyroscope, and together you may compute things, how fast your device is moving, what is the acceleration in a particular direction. All of those things can be computed, linear acceleration, rotation vector, a lot of these. And here you have a full list of what are the types of motion sensors you have access to. The philosophy, the way we work with these sensors is very similar. We get the sensor manager and then we get the sensor we want to listen to. So for this is an example for gravity sensor. And what does the gravity sensor do? If you go up here, you will see type gravity, force of gravity along the x-axis, y-axis and z-axis. We all know that gravity is actually, it's always going to be pointing down, it points towards the center of the earth. But what happens is when you have a device and you're holding it at a certain tilt, we're talking about gravitational forces, we compute, those are computed in which direction, what is the kind of force. So this force is known, but we are calculating the x, y, z components of it. So that's what this gravity sensor does. We listen to it, and then in the same way as before, you will implement a sensor event listener and you get events. Okay. So what is the difference between the accelerometer and the gyroscope?
Just by the names, I think that accelerometer is for acceleration of the device. So if you're using a Maps app, they can tell you most of the maps are how fast you're going, if you're going over the speed limit or not. Google Maps and a lot of these apps. And gyroscope, mm, uh, since it has to do with orientation, I think. So it might be with what's the device orientation. That's what I guess.
Right. Yeah, that's pretty much it. Accelerometer basically measures the current acceleration, current forces in a way, current forces acting on your device and what the resultant acceleration is. It includes the acceleration due to gravity. So you will see here type accelerometer. This is a sensor. So this is the computed sensor that is available to us. One is type accelerometer, acceleration force along x-axis, including gravity. Then there is one called linear acceleration. This is acceleration force along the x-axis, excluding gravity, because gravity is always present. So you very often, if you want to measure these things, you will want the one without the gravity, so that you're actually talking about what is being perceived, not what is actually happening in terms of physics, pure physics. And gyroscope, it basically measures the rotation, rate of rotation along any axis. That's what it does. So the gyroscope has to do with how your device is being rotated, and acceleration is how the device is moving, or up, down, any which direction, does not matter. And these together will form a basis for all the things that you do, the games there are games like, for example, games about driving a car where you will just tilt your device, you'll play with your device, you'll be using the device to make turns and all that. All of them will work using one of these sensors.
I think gyroscope is usually always needed with if you're using AR technology because you have to tilt your phone to see some preview and stuff like Pokemon Go, for example. Like if you move your phone up and down, you will see different view. So that's gyroscope is needed for that.
Yeah, yeah. Yeah, many things. Even, for example, I think some of the maps apps have this feature that you can move your app and the map itself orients along, how how your phone is being positioned. Yeah, many examples, many apps use this. So what we want to do today, our main activity today is where we stopped last time. We stopped at this. Right? We have this hello world. What we want to do though is we want to end up with this. This is the hello world thing, and we have a device position sensor here in the your sensors. So you guys don't have this yet. This is the demo I did for myself. And as we rotate these, it looks like this is not listening right now. Maybe I have to run it through the debugger. I have no idea. This is pre-installed. What happens is that this hello world, it moves depending upon how the device is. So if it is moving like this, depending upon the rotation of the device, your hello world text will move around on the screen. This is what we want to achieve. We saw it at the end of the class last time I showed it. So what I want to do is I want you guys to take some time, read this documentation, motion sensors, and suggest the best sensor to use for this purpose. And also we'll answer the question whether it's a hardware or a software sensor. So this page, motion sensors, has a list of all the sensors. So take a let's it's a pretty long documentation. I don't know how long you guys will take, but let's give everybody at least 5 minutes. So open this page, look at the types of sensors available and find out what is the best sensor to use. That will allow us to compute the position of this. That's what we want to do. We want to compute where on the screen this should be based on the device position. So whatever you think we need to measure, which sensor will give us that. So I'll let you guys do that. Take 5 minutes. It's 10:31. So you have, let's say, until 10:36. If you need more time, just say I need more time. We'll extend it. So at 10:36, I will ask if anybody needs more time and we'll give you more time. Let's do that. And this, if you Google Android sensors documentation, you should be able to reach that page. Otherwise, you can look at this. I can paste this in the chat. How about that? You can just open it. Okay, there it is. It's in the chat. You can open it and you'll be able to see it. So, you guys need more time? So we have one vote for accelerometer. Rotation vector. That's a good idea. As you're getting done, type your suggestion in the chat. And there is more than one way of doing it. So there's, there is not just one answer to this. There are different ways of doing it. Okay. So what we'll do is we'll resume here. And if you good. And if you're still reading, if you need more time to read it, please feel free to continue later on. So we'll move on with the class here. We have spent about 10 minutes on this. So the answers we have got, there are two choices, accelerometer, and the other one we got is rotation vector. So both of them could do the job for us, including the type gravity. So accelerometer tells us the forces along any axis. So basically, given those three components, the x, y, z component of the accelerometer, we could compute how the forces are acting, and we can actually compute what forces are acting on, that hello world and move it accordingly on the screen. So you could do it using this. You could do it using, well, gyroscope probably is not going to work because it computes the rate of rotation. What if the device is not rotating anymore? It's just stationary at a certain angle. So this won't do our job. But rotation vector will. So it measures, again, it's very similar to the accelerometer in that it measures the components along different axes. If we look into more details here, we'll find rotation vector sensor represents the orientation of the device as a combination of an angle and an axis in which the device has rotated through an angle theta around axis x, y, or z. This is basically a visual representation of the coordinate system that is used. So what this does is it allows us to calculate the magnitude in different directions. What we will do today is we will use the rotation vector to calculate. Where did it go? Rotation vector sensor, this one, to do our job, which is basically to calculate the angles and determine where to place the text. So both answers are correct. We'll prefer the rotation vector. As you will see, it allows us more easily to arrive at what we are looking for. And what is it? Is it a software or a hardware sensor? Rotation vector.
I think rotation vector relies on gyroscope, and gyroscope is a hardware, but it could be replicated through software as well if it's an old Android device and it doesn't have gyroscope, so using some other sensors, I think it's possible.
So rotation vector, it can be software or hardware. So some newer devices may have it as a hardware sensor, which you don't need to compute anything. But for our purposes, it does not matter whether it's a software or a hardware sensor. Once we implement using our sensor manager and listening, the output is the same. Underlying mechanism is not important for us. And let's see if this has any API requirements. So rotation vector is available since API level 9. We usually, when we start a new project, Android suggests API level 15. It covers 99% or so of devices. So it's good, we can use this. Some other sensors like significant motion, this kind of, see, this is a newer sensor. Stationary detect, API level 24, even newer. Anyway, depending upon which sensor you are using, you will have to see if your API supports it. And even if you don't check it, Android will complain to you. It will say, okay, you are using this API, but your project does not have the same API. So what was that? Stationary detect, right? Let me put this here. If I try to run this app, it will complain that your API needs to be higher. Anyway, I'm not going to do that right now. Oh, this is not the demo app. Let me close this one. The one we are working on is this. Okay, now that we know we are going to use rotation vector, what are our steps? So we'll use the rotation vector, and using the angles of the tilt, we'll place this. Hello world. So these are the steps. We have calculated angles. I think we are jumping ahead of ourselves here. The first thing we want to do is we want to start listening to this sensor. So what do we need to do in the code? We want to listen to the rotation vector.
Yeah, we need to get the type rotations vector. So just like how we're getting default sensor, so we can get a rotation vector as well. I'm not sure if we can do this in the same activity.
We will do it in the same activity, and then we'll see a combination of the two sensors working here.
Nice.
Okay. So what our steps are, we need a variable in which to keep the rotation vector and get it here. And there is one more step, which is to start listening to it, to register the listener. So why don't you all go ahead and implement that much? Pretty much 3 lines of code. You need to duplicate what we did for light sensor in terms of declaring and registering. So I'm going to do it here. If you haven't done it and if you want to follow along, you can do that. So we'll declare a variable to keep track of the sensor. We'll call it rotation vector sensor. And just like we did, we retrieved the light sensor from the sensor manager. We will retrieve the rotation vector sensor, same function call. And now we need to register, basically start listening to it. Pretty much the same function call. We are going to be implementing it in the same activity. And sensor delay normal. Okay, so we've got the rotation vector set up now. It will start sending events. Two questions. Where will the events go? Which function? When they're received. Exactly. They'll go to the same function. So it becomes our job inside this function to detect which event was received and what to do with it. So here we will have to start doing that. We'll come back to that. The second question I have is, we registered, right? Two sensors, each one separately. Do we need to unregister them separately, or is one function call enough? Okay, this is another something I want you to find out. Take a couple of minutes, do a Google search if you need to. Find out if we need to unregister one by one or one function call does it all. Okay, what's the verdict? Do we need to call it twice in the on pause, or one is enough? One vote for it's enough. Yeah, you guys are right. It unregisters everything. So we don't need multiple calls. Now,
It's possible to unregister individual sensor as well, because it might be a case where app you have to just unregister. So I saw it on Stack Overflow. You can do that, but it's just a little bit different declaration of the
exactly. So let's say you have an app, we are listening to these two sensors, and maybe one you want to keep on listening even when your activity is on pause. Then you can unregister just one sensor. So if we type sensor manager dot unregister, you will see that there is a function definition which allows you to, you can't see the full thing here, but it allows you to unregister a particular sensor. So you have both possibilities. In our case, we'll just use one function call because we really not going to do anything with the callbacks once the application is in the background. Okay. So now we are up to a point where our events are going to start, coming here. So let's find out what this sensor event it gives us. See, it gives us four things. Values. Values is what we used. If you look before, we used this values to get the illuminance. So all sensors return an array of floats called values, and whatever measurements they are taking, they'll return it in that array. If they're returning four values, this array will have a length of four. It will return four things. If they're returning two, it will have two, like that. So our rotation vector is also going to be received as an array. So we'll use that. But more importantly, right at the top of this, we know which sensor that reading came from, right? So let's store it here in a variable so that we can differentiate between the two. So when the sensor is of type light, we do this, whatever we are doing. And if it's of type rotation vector, we will implement what we need to do. So we need to enclose all of this, the code we already have, in an if block and make sure that is executed when the sensor is of this type light. So how do we do that? We'll say if sensor equal to if it is of the type light, okay, this is complaining, equal to cannot be applied to Android hardware sensor. So on the left is something of type Android hardware sensor. On the right is an integer. How do we compare these two to make sure? What would you do now if you saw this error? I'm going to close the if block so it will indent properly. Exactly. So we do sensor dot get type. Gets us the type of the sensor because the sensor object itself contains everything. Sensors types and any other attributes that a sensor is supposed to have. All of that is in it, but including the type. So we compare the type. And if it is this type, it will go here. Right? And since we are doing only two sensors, we can just say else and implement the rest. If you're doing more than two, then you will have else if sensor type is gravity, rotation vector, whatever you're listening to, you will implement all of them. In our case, right now we are at two. So basically, this is when type is rotation vector. Let's print here something, the values, something that we are receiving, right? So what does a sensor of type rotation vector return? In our documentation, rotation vector, it returns four things. So the float will have four values, index 0, 1, 2, 3, and rotation vector components along the x, y, and z axis. So what we'll do is we'll retrieve these three values and we'll print them. That's our first step. So float x equal to, just like we did here for the light sensor, we got value 0 because it returns only one value, or at least the only value we are interested in is the light meter reading. So here we'll do the same, values 0. So let's add these, and right now what we'll do is, instead of doing a lot more with it, we'll just print them out and see if we are getting the readings that we want. So we will do that, put it in the log, rotation vector readings. Make a nicely formatted comment here to print the values of x, y, and z. All right, so this, now when we run this app, we should start getting these readings at whatever frequency it is coming in at. Let's run the app. Go ahead and run your app as well. And we'll open the log here. So see, the log here is getting inundated with readings at a phenomenal speed. So between 28 and 29 seconds, you see it's almost every 10 milliseconds it is telling you what it's doing, what the reading is. And the reading is it changing? It is changing because my device is rotated, which means, let's just set everything to flat and then run this app again. So what happens is that this rotation vector, if your device was like this, what it means is, if you have, let's say, a little ball placed anywhere on the device, it has forces, it will keep on moving. That's what this is telling you, that it keeps on moving. And when I switch it back, it is, bringing that thing, it is going to asymptotically reach a value which is constant. Now, because we started, at least on my emulator, the device was tilted, I'm going to run this again and see what are the readings that we get from a blank slate. So they are basically pretty much zeros. 10 raised to minus 8, 10 raised to minus 8, minus 6. Very small. Okay. The main thing here is that have started receiving these readings. We are getting the X, Y, and Z, from the sensor. Now what we need to do is, if we go back to our slides, we need to convert those readings into angles. So So this is the kind of the calculation we will do, and you can choose something different as well. But what I want to do is we'll ignore any movement, rotation of the phone which does not change the forces, the two-dimensional forces acting on it in the plane of the phone. So there are three axes, right? There's one like this. So if my phone is tilted like this, if I rotate it around the vertical axis, the forces in the two-dimensional plane don't change. So the z-axis is what we'll ignore. We'll just keep x and y. And what we will do is, depending upon the angle, if the phone is fully vertical, I want that hello world to drop to the bottom. If the phone is perfectly horizontal, I want it to go to the center. If it is tilted like this, I want to go here, like that. And if there is a combination, if it is like this, then I want it to gradually, end up at one corner. So just like imagine if you had a ball here and you're trying to just, make it go dance around on the phone. That's what we want. So we'll work with angles. So if the angle is, depending upon the angle, we will decide where the hello world. And like I said last time, you could put an image of a ball there if you want to make it more interesting, and then you will see that ball moving. So based on the angle, we'll compute the angle. If it's like this, it will just drop. If it's like this, it will stay in the center. And if it was already here when you do this, it will start moving towards the center. And we'll see that being animated. That's what we want. So now we have the XYZ readings, but we don't have angles. Those XYZ, what they measure is the rotation vector component. So it gives you the value of this x star sine theta by 2. And what we want is we want actually the angle. How do we do that? So this is what we are doing. We have determined the right type of sensor. We are listening to it right now. And we have added the implementation to handle different sensors differently. So the next question to ask is how to convert the event data received from that rotation vector sensor to angles. Now this is complex mathematics. It's beyond the scope of what we are doing, mathematics and physics combined. So what we'll do is we'll rely on Google to give us that reading. So this is the search query you can use, rotation vector sensor, get angles. This is how I got it. And you should get in your results a document, a result, basically a page called calculating Euler angles. Roll, pitch, and yaw. Roll, pitch, and yaw is the name for the angle in each direction. So what is the roll, what is the pitch, and what is the yaw using this? And you should end up at this page. So, okay, I'm going to copy it and we'll paste it here. So the page we are looking for is not the first result. It's the fourth one here. Calculating Euler angles. Go to that page. So this is somebody's blog, I suppose, and the person was exactly what they're building, but it looks like this could be useful on something like a drone, for example. You could know how to which drone has multiple those propellers, which propeller to give more force to, more the speed, and that will determine the angle and the flight path and all of that. So what we want is we want to use this to calculate the roll, pitch, and yaw. So the code we need is, given the results, right? The way it happens is that you provide the vector to this, and it calculates a matrix, which is basically a 3 by 3 matrix. And that we convert into degrees. I'm going to tell you what I don't want to go into the details of this. Those of you who have an interest in physics and how it actually is happening can read this, maybe even some more background information. But for our purposes, what is sufficient is this part here. We need this calculate angles function. And we also need to declare these variables. These two variables need to go at the top in our code. So what we'll do is we'll basically, let's just copy this whole section here, and we'll paste it in our code. You can paste it at the bottom after the last function we have right now. What did this do? It declared the two variables as class variables, and it got us the function. We still have some problems. Remap is missing. What is all this? We'll get it from another section on the same page. So what we are missing is this calculate angles. Let's get this part as well. Convert to degrees is not here. Get this. In fact, I think we could have just done with this one here, but anyway, too late for that now. So convert to degrees has come here. And this, what it is doing is this, according to the rotation of the device, is changing something. So just comment this line out that has remap X and Y. We'll come back to it. We'll see how this much, what the behavior here is. Any questions here? Why we are doing this? Yes. So from this page, what you want is basically copied this block here, the second block of code, and we added this function to it as well. Okay. How about this? We leave it, I'll leave this open here. So if you're still looking at it, you can do this. And we'll take a break here. We're at 11:15. We'll take a 20-minute break. And in the meantime, some things to ponder for you. Why did we declare these variables here? How are they being used? We are passing this as an argument here. And this line that I commented out, if I uncomment it, you'll see that again we pass it as an argument, and this R matrix goes as another argument. What is going on here? Something for you to think about. And we'll resume at 11:35.